Okay.
Okay.
You're on.
Cool. Okay. Yeah. First of all, thanks again to all the organizers and the lecturers for this. I think would be a memorable experience for all of us. So it's really enjoyable. And today, in this talk, I will talk to you about the what was some of the results from my postdoc, and as a few concerning a recent class of approaches for high-dimensional functional approximation based on compressive sensing. In particular, we will focus on the scenario where your samples or your queries are affected by unknown sources of errors. And there will be many analogies with the lecture of Professor Cohen. So I think it will be useful for us to tackle this. We'll see how to tackle this problem for a slightly different angle, but there will be many similarities. So the problem we are going to study is the following. So you want to approximate a function defined over a high-dimensional tensor product domain from some pointwise samples of f. Rules of the game are the following. We are free to choose our sampling points Ti. These may also be expensive. For example, they may depend on PDE solves, like in uncertainty quantification. And particularly in this talk, we'll be interested in the case where these are corrupted by several sources of errors, like, for example, numerical error, physical noise, model error. The underlying assumption will be to have some compressibility of f with respect to some orthogonal polynomial basis. And I'll give you more details in a while. Of course, the main challenge is the curse of dimensionality. And as we've seen, one of the most prominent applications is UQ. Let me just mention there is a nice community of people working on this problem. So the first steps combining compressed sensing with orthogonal polynomials were made in 2012, but also some applied mathematicians and engineers started playing with UQ and compressed sensing since 2011, 2012. And that's the main focus that we'll have today. So methods based on compressive sensing. And let me describe the methodology. So I will show you some theoretical results and some numerics. And let me talk about the methodology that we'll be able to formally analyze. So first we need a sparsity basis, of course, to expand our function. And this will be, in this talk, a tensor product family of Chebyshev or Legendre polynomials. As it's usual, then we have an infinite expansion. Of course, we need to truncate this expansion, and so we need to pick a finite dimensional multi-index set lambda. And then here we are firstly introducing a first source of error, which is a truncation error that will always affect our samples. And this is the approximation to f that we will be aiming, that we will try to compute. Call it f lambda and e lambda, the truncation error. Then how do we pick our samples? So we are free in this setting to choose them. As in the lecture by Professor Cohen, we will pick them at random. In particular, we will sample these points according to the same measure that makes the orthogonal polynomials that we are considering an orthogonal family. So we will call this measure nu. And then we assemble our so-called design matrix in this context on our right-hand side by just evaluating the basis functions and the function f at our sampling points. And we get our linear system. There's also this technical issue of rescaling that's due in compressed sensing to having the so-called restricted isometry property to have a nice behavior of A transpose A in expectation, essentially. And so here we will have a corruption of our samples by an error vector that we will call E in this context. How do we compute our approximation? Now we have our data. And we will consider a special type of sparse regularization, in particular weighted L1 minimization. So the first decoder we are going to analyze is the so-called weighted quadratically constrained basis pursuit decoder. So we minimize the weighted L1 norm of the coefficient vector Z subject to a constraint on the data fidelity term, up to a certain tolerance eta. And we solve this problem. That's a convex minimization problem. We solve it, and we have our approximation f hat, plugging in the x hat, the solution to this problem. We will also adopt a specific choice for the weights that allows us to prove some theory, and we'll have some advantage, as we will see, particularly the L infinity norm of the basis functions. Now, why weighted L1 norm? Because I will see this will allow us to promote a particular structure in the set of coefficients. This was also presented the lecture by Professor Cohen, the so-called lower or downward closed set structure. So just recalling you that we want to see this kind of staircase behavior. Okay, we don't want to see bulks or holes in our multi-index set. And since we are using the weighted L1 minimization norm, we will also measure the performance of our decoder according to this norm, the weighted L1 minimization norm, and our target accuracy will be the following: the best S-term approximation error with respect to lower sets measured to this with respect to this norm. So given a vector of coefficient x, this will just be the best error you can achieve by S sparse vectors that are supported in a lower set. Why? So lower sets are highly used in high-dimensional functional approximation, UQ. So in this particular context with compressive sensing, they will have two main advantages. First, and the first one is shared by many methods, compressibility. So it is possible to show that for a large class of parametric PDEs, the best S-term approximation error in lower sets has very nice decay rates, and usually it's comparable to the best S-term approximation error for smooth PDEs. And the second property that would be even more important in our context is the following. So if we consider the union of all S-sparse lower sets, well, then we get a very well-known set. That's the hyperbolic cross of order S. And this will be our universe, so our ambient space, the lambda, where we are looking for an approximation that is comparable with the best S-term approximation in lower sets. So if you never met the hyperbolic cross, that's it. So in 3 dimension, for example, S order 3, 5, 9, 17, this set contains all the S sparse lower sets. Okay, the union of all this supports. Okay, now we have all the ingredients to formulate some theory, some recovery guarantee. So there was this first result that I want to mention here due to Abdullah Shkifa, Nick Dexter, Hong Tran, and Clayton Webster. So if you know an a priori upper bound to the noise level, given some, you have the upper bound eta, and then you, assuming a certain sampling complexity, so forget about all these log factors. At the end of the day, what is important is that you have this algebraic scaling between the number of samples and S, the sparsity you would like to, the target sparsity, where the exponent depends on the particular polynomial family that you're using. It's 2 or 1.58, roughly. So in this huge log factor, the good news is that you only see a log D, essentially. So that this is why this approach can substantially lessen the curse of dimensionality in this context. Well, under these assumptions, you can show that you can compute an approximation f hat to your function f. For example, you can prove a bound in respect to the L infinity norm, and you can achieve the target accuracy, the best S-term approximation error in lower sets with respect to the weighted L1 norm, plus another term that is due to the noise corrupting the samples, and that coincides with this upper bound. So here we are considering the tuning parameter of our decoder. So we are tuning this parameter according to this upper bound. And however, this may not be, usually in practice it's hard to find such an upper bound. So for example, you always have the truncation error you may have other sources of errors, like numerical error due to the particular PD solver you're using, or some kind of model errors. So the first question we wanted to tackle was, what can we say without assuming any a priori knowledge on the noise? So both in theory and in practice. And this is the first work in collaboration with Ben Adcock from SFU and Clayton Webster, from Oak Ridge National Lab. And so you can have a similar recovery guarantee. However, so you have the analogous sampling rate with respect to the noise-aware scenario. Now we are in a so-called noise-blind scenario. However, without making assumptions on E, you can still prove robustness of this approach. So you are disentangling how you tune your decoder from any upper bound on your noise. And so you just have a slightly more complex right-hand side here in the recovery guarantee. So still now you have the eta, which is just the tuning parameter, but not necessarily an upper bound to the noise, the level of noise again. And this third term, this is interesting because it tells us so it suggests what is the optimal way to tune your decoder, because now you would like to make this term as small as possible. So it suggests that eta should not just be an upper bound to your noise, but you should try to calibrate it as accurately as possible to the level of noise to optimize the performance of your weighted quadratically constrained basis pursuit. Then this term, which measures this mismatch, is also amplified by this constant, which is log factor in SD epsilon, which is also, actually the probability of failure. All these results are in high probability. An algebraic factor in S, and also we have this minimum singular value of our design matrix. That's also nice because it's explicitly computable. And so let's just comment more on this result. So yeah, we can get rid of this assumption. Still robustness is observed. This term suggests an optimal tuning strategy that, for example, justifies the use of cross-validation to estimate eta. Moreover, this minimum singular value is playing a role in the recovery guarantee. You can show that behaves well in expectation. Unfortunately, it's in general, quantifying this in probability is not that easy for boundary orthonormal systems. It can be done for random Gaussian matrices, but it's more tricky for in this context with orthogonal polynomials. And however, this constant Q amplifying this mismatch as moderate size from the numerical viewpoint. We won't go into the details of the proof, but let me just mention that the main ingredients used here are the weighted versions of the restricted isometry property, standard in compressive sensing, also the null space property, and this quotient property introduced in 2010 by Wojciech in the context of compressive sensing. But still, we have a problem. So, okay, we can suggest an optimal tuning strategy for our decoder. However, this optimal tuning strategy still depends on the unknown error. So, second question we wanted to tackle, can we get rid of the dependence of the tuning parameter on the error at all? That's the second question we answered. This is in collaboration again with Ben Adcock and Annie Bau, who's now a graduate student at University of British Columbia. And yeah, so the approach we had was the following. Let's just try to change the decoder. So first option, let's consider the following two unconstrained decoders. The first is very popular, the lasso, in its weighted formulation. Where we just have a data fidelity term plus lambda times the regularization term, which is again weighted L1 norm. And the second option is slightly less popular. So again, it's quite popular, at least in the unweighted case in statistics. It's not as popular in compressive sensing and functional approximation, we found. So in the second decoder, there's just a tiny difference. We get rid of this 2. This exponent 2 in the data fidelity term. Looks like a tiny difference, however, it will make a remarkable there will be a remarkable qualitative difference in terms of recovery properties of this square root lasso decoder with respect to the lasso. So we can show similar recovery guarantees, and again, the sampling complexity is the same as in the previous results. We have that long log factor, depends only logarithmically in D as before. And let's also take a look at the recovery estimates. So again, L infinity norm, even though, by the way, everything can be also proved for the weighted L2 norm. So okay, in this case, L infinity norm, so again, our target accuracy, the best external approximation, error in lower sets plus the noise level. But more interestingly, let's take a look at the tuning parameter strategies suggested by the theory. So these are really kind of, the proof is forcing you to making these choices through the theory. If you go through the proof, if you're interested, check out our paper. And in the weighted lasso case, still we have a dependence on the norm of the noise. However, more interestingly, in the square root lasso case, this is removed. So the optimal tuning choice just depends on S. So still, we need some a priori information. We need to know which level of sparsity we are interested in, but we got rid of the noise level in the tuning parameter. And by the way, in this approach, S is kind of by design an input parameter because also determines the size of the hyperbolic cross you're exploring. So it's not a big deal to have this dependence here in this particular case. And yeah, also good news, that's more technical, but the noise is not amplified by any log factor in this case, as opposed to the weighted quadratically constrained basis pursuit case. Okay, so let me show you some numerics. So you can actually verify this in practice. That's just a toy example for functional approximation, very smooth 15-dimensional function, and we plot the recovery error as a function of the tuning parameter. So we run our decoder for multiple choices of eta or lambda, depending on which decoder are you working with. Different colors, sorry, this is not readable here, but different colors correspond to different levels of noise that we are injecting into the samples. So blue is noise 0, just truncation error. In this case, green 10 to the minus 2, red 10 to the minus, green is minus 3, red minus 2, black minus 1. That's with Gaussian noise, but the same holds also with uniformly distributed noise. And so you can see we always observe this global minima, which correspond to the optimal choice of the tuning parameter. Okay, so if you're able to find this global minima, it means that you're able to get the most out of your decoding strategy. And in particular, in the highly noisy scenario, here we're injecting noise norm 10 to the minus 1, it's particularly beneficial to tuning your decoder carefully, because you can gain, for example, an error reduction up to a factor 7 with the black curves. However, so the interesting fact is that these global minima are shifted for the first two decoders, the basis pursuit decoder and the lasso. So they depend on the color, they depend on the noise level. However, they are also numerically aligned for the square root lasso. So again, we observe that this independence is also realized in practice. Let me also briefly discuss an example from parametric PDEs. So that's a parametric diffusion problem where the diffusion coefficient is piecewise constant on each one of these circular inclusions, and we are observing as a quantity of interest the integral of the solution and the central square, for example. So our samples depend on PDE solves, and the error here has different contributions, numerical error, numerical error, model error, depending, for example, the mesh size you're using to discretize your PDE, and so on and so forth. And so we can also observe that so we compare the performance. Now we plot the recovery error as a function of the sampling complexity and the number of samples we are considering. And so, okay, all the three decoders, substantially they have this similar performances because everything is in level 10 to the minus 3. Square root lasso is slightly better, but not substantially. We go from 1.6 to 2.4, 10 to the minus 3. However, again, in the first two curves, in order to optimally tune our decoder, we need to estimate the error. So for doing this, we use a high fidelity solution, and then essentially we use it to compute the norm of the residual, and then we define the tuning parameter accordingly. However, for the square root lasso, we're just using the choice suggested by the theory. Okay, so we can get the optimal performance without injecting any a priori knowledge on it. Okay, let me also observe in passing that you can tackle another interesting problem with this machinery of compressive sensing for functional approximation, in particular the case of sparse corruptions. So if you have some corrupted data, so for example, if you're running your simulations and you compute each sample on a different node of a cluster, some of these nodes may fail. So you will have like some of the samples which are essentially unusable. They're just they're just noise. In this case, you have the corruption term has a bounded part which contains numerical error, model error, and so on, and a sparse but possibly unbounded part which is due to node failures. So if you have an estimate, so now you need some a priori information here. You need an estimate of how many nodes are failing, you think are failing. Like maybe you have an idea, okay, let's say we think 20% of them are failing. Of course, you don't know which ones, but you need to know something about the percentage of them. If you know this, then you can run everything in a so-called fault-tolerant fashion. So the method is robust to this kind of corruptions. And you just need to modify the decoder. It's the data fidelity term. You consider the L1 norm instead of the L2 norm. And this, again, promotes sparsity in the corruption term. And that's called the lat lasso or weighted lat lasso in this case. And again, I will not show you all the details, but you can prove a similar recovery guarantees. And the good news is that you don't see the sparse, possibly unbounded corruption in the recovery guarantee. You just see the bounded part. So that's kind of a miracle of this lat lasso. It just gets rid of the sparse corruptions. Similarly to the comprehensive case, when you can get exact recovery, if you have an exactly sparse vector. Okay, so this brings me to the very final part. Let me outline a couple of future challenges in this field. So first we have seen we have a certain complexity, simply complexity rate s to the power gamma. So first question is, can we make this gamma 1? So like in compressive sensing, can we have a linear scaling between M and S? That's an important open problem still. This may require introducing new theoretical tools in compressive sensing, or maybe performing the sampling in a more accurate way. Also, can we benefit? So, okay, at the beginning, compressive sensing was kind of sold as a totally non-adaptive strategy, but it turns out that you can gain something from adaptivity so choosing the samples like in different batches and adapting the samples based on a more and more accurate estimate of the support of your function. We have some preliminary results with Ben Adcock and Claire Boyer from Sorbonne Université that promising in the sense that you can do adaptivity and estimating, so having a better estimate for the sampling measure and the support of your unknown function at the same time. This is possible thanks to sampling complexity estimates that depend on this unknown support of the signal. It is possible that you can derive this kind of inequalities. And yeah, so third one about the sampling part, also, is there a notion of optimal sampling here? Again, we are sampling according to the orthogonality measure, but we have no guarantee that this is optimal in any sense, so that's still open. And let me also talk about the recovery phase. So, okay, I'm telling you, yeah, we're running this nice convex minimization program. However, the universe where you're looking for the sparse signal can be very large. If you're really running a large-scale simulation, then your hyperbolic cross, although very efficient, can be nevertheless too large. So that's maybe the main challenge to tackle for compressed sensing in general. And I think a promising avenue here is, so of course you need to either exploit some structure, some more structure in the recovery, or introduce some kind of randomization. I don't know, this is still an open problem. I think the greedy strategies are, or some variation of structured greedy strategies can be a nice avenue here to investigate more. We have some preliminary numerics about a weighted version of orthogonal matching pursuit that can be way faster than weighted L1 minimization. Still, you touch the dimension of the large space if you don't play any trick with structure. But nevertheless, like, you have a number of iterations that scales linearly with the sparsity, and also a way more easy parallelizability of your method. And again, it may be adaptable to, for example, taking into account the lower set structure during the search. This is something that I think can be really interesting. I think, yeah, this brings me to the conclusions. These are a few references, and thank you very much for your attention.
Thank you, Simone.
My questions.
So, the decoder, so the decoder will not necessarily generate a lower set.
No, that's correct.
So you mentioned lower sets, so you use them actually more in the theoretical analysis than in the
right,
which is okay. I mean,
exactly. Actually, that's a great remark. I think that's also related to this future direction. I think we need to take into account that structure more directly in the optimization part to speed up.
The main observation you start with is because you have this lower set, you can search within the hyperbolic cross.
And also, yeah, we can recover. So yeah, what we compute.
And then you have a little bit improved recovery.
So you can kind of achieve the best standard approximation error in lower sets with a vector that, the output of the convex minimization is not necessarily supported on a lower set. But
maybe it could be a bit, it could be a bit of a headache to try to devise a notion, a recovery, and one kind of recovery that at the same time is automatic. Do you have an idea how you...
I think, like, more than, I mean, not really convex minimization, but more like greedy approximation.
Okay,
Yeah.
Like OMP sort, but you would just go...
Yeah, OMP, kind of structured OMP somehow.
Okay.
Yeah, if you want to preserve that kind of structure.
So when you consider the total numerical cost,
yeah,
it seems to me that rather than improving, say, S to the gamma to S to the 1, the large dimension, is that more of a limiting factor, actually?
So sorry, you mean the dimension of the hyperbolic cross?
Yeah.
So again, so here, that's the limitation from the viewpoint of the recovery. Yeah. So like this series shows you that you can break or lessen actually the Cursor dimensionality because you still see a log factor in D from the sampling point. But yeah, you're right. The decoder still depends on this dimension of the hyperbolic cross that has.
So your computation always scales.
Yeah, exactly. So that's still, you have upper bounds for the dimension of this hyperbolic cross, but still, this for large D, this scales badly with D.
This is where the D will kick in
the computational cost, exactly. Yeah, that's the most.
So, but your input parameter, your tuning parameter is really the S, right? It's the S, the sparsity.
Yeah.
At that point, you don't really know what the best n-term approximation, best S-term approximation is going to be, right?
So I mean, the advantage of this is that you're looking for the best S-term approximation error in lower sets. You don't know where the optimal lower set is, so you consider it.
But you guess the S.
Oh yeah, the assets. Yeah.
So you at a given point you don't really know what the accuracy.
I mean,
is.
yes, there's a missing link in the theory here. Actually, you should also estimate the decay rate. That's something we are actually doing right now. Like, it's not a main challenge, but it's just something that has not been written down yet. Actually, computing the decay of this with respect to the weighted weighted L1 norm respect to S for a certain class of functions, and then you can guess the S. So I mean, you can choose the S
but
based.
to find the best S term and to check it what it is, I mean, you again have to look at the long signal, right?
I mean, the output here is the output. This X hat is still n-dimensional with the convex approach.
Why wouldn't you just solve it for all S and then double S?
And then guess and then extrapolate the rate.
Going until you achieve whatever accuracy.
Actually,
But he doesn't, for any given S, he doesn't really have a bound on the actual out.
He doesn't have
You-
a posterior.
Yeah, he doesn't have an a posteriori bound.
That's something.
He
I mean,
doesn't.
Well, then you better do that.
Yes. But that's a general problem with non-intrusive methods.
yeah, right.
In intrusive methods, we have rigorously from coarse to fine with optimal complexity rates, everything. But
Yeah.
it's a fully intrusive method. But in the non-intrusive case, this to me seems a principal problem. Okay. Okay. Thank you very much.
Welcome.